Hello, students. No affiliation with any institution here. Um, I am going to cover doublets of triplets or quartets or doublets in this video. Um, I hope this is useful for you guys. I just literally made a video earlier of this, and I apparently didn't screen share. So if I am not enthusiastic right now, then that is why. Anyways, um, so the doublets of triplets, the things that we were talking about. Hopefully, this is screen sharing, right? I just gotta make sure. Okay, it is. All right. So yeah, so just to cover doublets of triplets, um, so let's kind of start off again. Hopefully, you do realize that a doublets of doublets arises because of a presence of a chirality center. So the triplets is just an addition to that. Okay. So let's kind of draw structure. The top of my head. Let's just draw this one. This should be sufficient enough. Or let's have it like this. Let's kind of call this just R. Let's say that this was an OH. Why not? And let's say this is H. Okay. Right. And let's just say we terminate this with a CL. Because why not? Right. So hopefully from that you're able to recognize that this is your chiral center here. And so let's say that this is your HA, and let's just say we have HB and HC, HD, and HE. Okay, so let's first look at the multiplicity of HA. Okay, let's look at the multiplicity of HA. Let's actually just consider this as another chloride so that there's no confusion. So multiplicity of HA, hopefully you understand that the only neighbors of HA is HB and HC, but you know that they are chemically inequivalents because of this chiral center, right? So the carbons adjacent to the chiral center, so the thing that is adjacent, so this is adjacent, the blue one is adjacent to the chiral center. Because of that, HB and HC will be chemically inequivalent. And because they are chemically inequivalent, oh, sorry, let me backtrack. So because of this chiral center as well, your JAB will not equal JAC, right? Will not equal JAC, all right? So hopefully you understand this is a doublets of doublets. Okay, so that's kind of the first thing there. And now let's talk about the multiplicity of HB. Let's talk about HB. Okay. So let's, for example, right, let's just kind of scratch this out, right? Let's say this wasn't a molecule, right? And let's say that this was just a Cl, right? Based on our notes, you know that HB would have been a doublet of doublets. And why is that? Because it will couple differently from HC and HA because of the chiral center that is bound to HA, right? So you know that it's a doublet of doublet. Now, where does the triplet come from is the question. And so you know that this is your chiral center, okay? So it's the carbon adjacent to it that makes it chemically inequivalent. But according to kind of and kind of for the purposes of this class, that means this one is not affected by this chiral center, right? It's too far. And so HD and HE will actually be chemically equivalent. So HD and HE are chemically equivalent. Okay. And so because they are chemically equivalent, they will also have the same coupling constant with B. All right. Okay. Okay. Oop. Anyways. Okay. So hopefully that made sense. Whatever. Anyways. So let's say, for example, right? Let's say you kind of scratch this part out, right? Say you scratch that part, and right. Let's say you don't have a chiral center there, right? Let's say that this was just a CH3, like normal. Okay, let's say that's it. Okay, so because there's no chiral center here, so HB and HC would be equivalents, and you will see that HB would just consider this as a triplet because they're chemically equivalent. So if you kind of put that all together, I mean, you could draw the entire like tree diagram to convince yourself, but it's too hard. It's even too hard for me. Uh, but you know that this thing right here, these will be chemically equivalent, so that produces a triplet. Okay, so you would have a triplet from HB, and you know that this thing causes a doublet, and this thing causes a doublet for you. And if you just put it all together, you literally just put it all together, it's a doublet of triplets. And so hopefully that made sense. But let's say, right, let's say you're in this kind of dilemma, and you oh sorry, let's try and see other examples too. So how can we get a quartet, for example? So we would just have to adjust this as having another H, actually. So this, if this was HF here, HB would become DDQ, because this becomes, again, if you remember, 3 neighbors is a quartet. And then this one, again, for the triplet, it was 2 neighbors, given that it was bound to a chloride there. So you get the triplet here, you couple here differently, you couple here differently, you couple with HD and HE the same. So these would cause a triplet, and hopefully that made sense. And then with the quartets. Also just something I do want to kind of note here. So let's say, for example, you had this sort of let's just make it so that this one, let's say that this was the OH here, and this was your H. Let's say that this was a Cl, and this was a let's say just bromide or whatever. Anyways, okay. So let's talk about the multiplicity of HA here. H. So let's talk about again. Hopefully you understand that you have these sort of invisible hydrogens. I guess I call them invisible hydrogens because in an organic skeletal thing, you don't they don't draw it the H for you, right? So these are I term them invisible hydrogens. If we if you want to make a movement and start calling them invisible hydrogens, that's cool. To say I coined it. Anyways, let's say you have H, E, and F here. And so what's interesting is, again, this is your chiral center right here. Okay, so that's your chiral center. Let's do it yellow, so it's just kind of the same thing. Chiral center, again, you have different substituents all around. So that's your chiral center. And so this chiral center will render HB, HC differently. It will also render HE and HF differently. So these will be chemically inequivalent. And because of this chiral center too, you know that the JAB is not the same as JAC, and this JAE is not the same as JAF. All right. And so that means you hopefully, just to convince you, the HA here, it will just produce a doublet here, a doublet here, a doublet here, a doublet here. You could draw the diagram too, but because of this fact that they have different J couplings, if you have different J couplings all the time, you're gonna create another doublet, if that makes sense. Okay. So you're really your multiplicity of HA is D D D D. Okay. Okay. So just to go back to this one here. So for example, right? um, we're still talking about HB, okay? Let's talk about HB. So I know that your top hat does say that if there's a chiral center anywhere in the molecule, it renders everything different. And that is true, okay? But in terms of co, just to keep it simple, we consider these chemically equivalents because it's not directly adjacent to the chiral center. So the thing adjacent to the chiral center is this circled one right here. And so let's say, for example, you want to consider this chemically inequivalent. They have different couplings. You could definitely do that, to be honest with you. I've seen him awarded such that. So again, just by the same logic as this, hopefully, as long as you, okay, so let's think about HB here. You literally have one neighbor, two neighbors, three neighbors, and four neighbors, and you have a chiral center. You could literally, again, like you gotta see the pattern, right? I'm such a patterns person, right? If you have a chiral center here and you're thinking about HB, just look at how many neighbors it has. And this is your doublet, that's another doublet, that's another doublet, doublet. You could also just call this doublets of doublets of doublet of doublet. And I can guarantee you, he'll give you full points too. As long as you, yeah, I like even the TAs will probably give you it. And that's the most accurate answer actually. The more accurate answer is four doublets. The reason why we or like for example, Co doesn't do that or like he do that. Or the main answer is usually DDT is because with a usually you don't have that strong of a NMR machine, and so you would see this triplet as a DD. So you would kind of see this as a, you will see that as a triplet in a weak NMR system. So hopefully that made sense. Hopefully this was useful. And this is try two. Hopefully it's synced in. Hopefully you guys can see the screen. Anyways, um, yeah. Cheers. Bye.